Welcome to my friends. Today's lectures. Now we are going to discuss the topic molecular orbital theory. In these topics, now we have going to discuss the point the energy level diagram for polyatomic molecules like angular hydrogen S3 plus molecules. Angular hydrogen S3 plus molecules. It belongs to the point group is D3H. You know that S3 plus molecules, it can be detected in electrical discharge through hydrogen gas in 1996. But it is experimentally found that the structures of S3 plus ion is to be equilateral triangular with H bond distance which is found to approximately 1 angstrom. But when these linear S3 plus S3 species can bend as like triangular S3 plus, the energy 1s orbitals they will further reduce to better overlap between the 1sa, 1sb and 1sc atomic orbitals as like three hydrogens like 1sa orbitals, 1sb orbitals of second hydrogens and 1sc orbitals, atomic orbitals of third hydrogen. So these energies of thrice sigma orbitals will decrease as a result of slightly overlap between these psi1 and 1s orbitals of third hydrogen, right? And therefore it bent and to get the triangular molecules. But you know that the energy of twice sigma molecular orbitals in triangular S3 plus ions, it increases slightly and it becomes going to antibonding molecular orbitals. The A1 orbitals, it has slightly symmetrical orbitals and therefore this 1 sigma is distinctly bonding, whereas E is a doubly degenerated orbitals how mix as like non-bonding and anti-bonding molecular orbitals. But the characteristics between the different pair of atoms and their net characters is antibonding as the energy is increased. But it's experimentally found that the S3 plus ions is a triangular ion and it has twice sigma and thrice sigma. They will have the same energy and therefore the electronic configurations or the order of the molecular orbitals, they should be the 1 sigma is less than twice sigma is equal to thrice sigma. So this type of relation we are shown in these diagrams. We clearly observe that it is 1 sigma, twice sigma and thrice sigma molecular orbitals. For is a bent for those molecules. So three hydrogens are there. One of these, second, and this is a third molecular orbital as like. But in polyatomic species, the word we are not use as a sigma, use as a word is a A. A is a non-bonding molecular orbitals. E is a doubly D degenerate orbitals, and capital small t we are is a triply degenerate orbitals. A for non-degenerate orbitals, non-bonding, sorry, non-degenerate orbitals. E for doubly degenerate orbitals, and small t is the triply degenerate orbitals. But in these diagrams, we clearly show that these three molecules we can bend like S3 molecules. We have considered as like this is a H1, this is HA, this is HP, and this is HC as like. Now we have see these three orbitals are greatly overlap with each others, but it is a twice sigma molecular orbitals. We are observed that it is a non-bonding molecular orbitals and it is a anti-bonding molecular orbitals. Means it is a doubly degenerate orbitals, or it is a mixed orbitals, right? It is uh, A1 orbitals, right? Slightly symmetric. Why it is symmetric? Because it is distinctly bonding, but E is a doubly degenerate orbitals, which is mixing orbitals, which is non-bonding and anti-bonding molecular orbitals, right? But these pairs, which pairs is non-bonding and anti-bonding pairs, molecular orbitals, the net characters is anti-bonding. Why? Because this is twice sigma molecular orbitals and thrice sigma molecular orbitals, they will have the same energy. But one sigma orbitals, it is a less energy from this because those molecular orbitals E doubly degenerate orbitals will shows character as like antibonding molecular orbitals. From these molecular energy level diagrams for H3 molecules, which are shows that the energy they will decrease by removing the one electrons from this non-bonding electron, right? Twice sigma electrons can remove. So bonding molecular orbitals will get 2 electrons only, right? So atomic orbitals for this H and atomic orbitals for this twice H. So these two electrons from the psi1 and psi2 having a group orbitals which are come here, and to get one sigma orbitals as is a, right? Means this is a type 1 sigma orbitals. But we observe that these one electrons which cluster with other two orbitals is greatly, right? So these two electrons which are come here and to get anti-bonding, sorry, bonding molecular orbitals are shows like a, and doubly bonded, doubly degenerate orbitals which is 2 sigma and thrice sigma molecular orbitals which having a same energy, but it is a it is a non degenerate orbitals will have the very lower energy than these orbitals. From these molecular energy level diagrams, we can calculate the bond order for H3 plus ions, which is found to be 1 because it contains 2 electrons in bonding molecular orbitals, and anti-bonding molecular orbitals or doubly degenerate molecular orbitals, they will be no electrons, right? Now we can find the bond order for these H3 plus ions by using the formula 1/2 bonding minus antibonding. So 1/2 2 minus 0 is equal to 1. But we can use a Walla diagrams. You know that Walla diagrams? by compare and assess the relative energy of different possible structures. So in Vallar diagrams, we can calculate the energies for those molecular orbitals and the plotted the value of metrical parameters as like the bond length or the bond angles. Then we clearly observe that how will you affect this energy by these H3 linear molecules is convert to H3 plus ions. Therefore, the amount of stabilization or destabilization of molecular orbitals is based on the amount of increase or decrease in phase overlap of atomic orbitals which are used to make each molecular orbitals. So these Vallar diagrams, we clearly observe that how will you change the energy, right? So those Vallar diagrams which shows that these bond angles versus 180 linear molecules and it is 60 degree. For benting, it is a triangular molecules. So energy for these triangular molecules will decrease and at linear molecule they will be increased. So see this difference. Now we have learned the molecular orbital diagrams of these S3 plus linear molecules. Now we have C and triangular S3 plus ions also C. From these two diagrams, we observe that the linear H3 plus ion has one field bonding and one anti-bonding molecular orbitals and one bonding molecular orbitals with the unpaired electron. But in triangular S3 plus ions found that one bonding and two degenerate antibonding molecular orbitals. And therefore electronic configuration for linear ion of S3 is 1 sigma 2 and twice sigma 1. But in case of triangular ions, we observe that we cannot use the label sigma. Therefore, the label can be used as small a, small b, or sorry, small a, small e, or small t, as like the labeling orbitals in nonlinear molecules, nonlinear polyatomic molecules on the basis of symmetry. The small a are used for the non-degenerate orbitals, small e are used for the doubly degenerate orbitals, and small t are used for triply degenerate orbitals. And therefore, electronic configurations for these triangular S3 plus ions is A twice, A2. Why it is a 2? Because these non degenerate orbitals, they will contain two electrons, right? So these diagrams, small a, this is a energy level diagrams for this linear S3 molecules and these energy level diagrams for S3 plus ions. Now we compare these two diagrams, we observe that it is a sigma and it is twice sigma. It contains the electronic configuration. Now see here the 1 sigma 2 and twice sigma 1. So 1 sigma 2 and twice sigma 1 electrons. So total 3 electrons are there. But in S3 plus ions we observe that the 2 electrons like A2, right now A2, so 2 electrons which is present in the non-bonding degenerate molecular orbitals and two antibonding the doubly degenerate molecular orbitals. Only 2 electrons, therefore A2 electrons which is present. And therefore, so such labelings as like A for non-degenerate, E for doubly degenerate, and T for triply degenerate orbitals. So this labeling can be used for to give an electronic configuration of the triangular ions. So these two diagrams of linear molecules and non-linear molecules we shows. So how will you change this energy, or how will you change these molecular orbitals to degenerate molecular orbitals, right? So as the bond angle changes, right, linear molecules found that the bond angle is 180-degree, like linear S3 molecules, and we can bend those molecules. The bond angle can change to 60-degree in triangular ions. The energy also of the molecular orbitals can change, like the sigma orbitals of linear ion can be converted into A and E orbitals in triangular ion, right? We have seen in last pictures of this molecular energy, molecular orbitals. So linear molecules we show sigma orbitals, and these sigma orbitals of linear molecules can change into A. A means non-bonding degenerate orbitals, and E is the doubly degenerate orbitals in triangular. Therefore, in Walsh diagrams, the energy calculation can show that the triangular species which is stable than S3 by using spectroscopic data. So by spectroscopic method, we can clearly distinguish between S3 linear molecules and S3 triangular molecules accordingly their energies. And it also can be seen from that these A molecular orbitals spread over all the atoms, right? So these A type molecular orbitals spread over all the atoms. It means that the two electrons bind the entire cluster together. Two electrons bind the entire cluster together. So such diagrams now we have seen here, right? Uh, 1 minute. So this A. So this one molecular orbitals which can cluster all these molecular orbitals, right? So those molecules or those molecular orbitals we can cluster all these group of atoms. So this is A. So these A molecular orbitals spread over all the atoms. So two electrons bind the entire cluster together. But this shows that molecular orbitals which can be delocalized orbitals, right? A type molecular orbitals, they are the delocalized orbitals, and therefore S3 plus ions can be described by the 3 center 2 electron bond. Why it is a 3 center 2 electrons bond? Because is 1 2 3 3 centers, right? Right, is it is a triangular as like we have considered as a like this. So 1 2 3 electrons, sorry, 3 centered, and they will present 2 electrons. Which is 2 electrons which is present in only A degenerate molecular orbitals, right? So this was diagrams for S3 plus I species. We observe that this A and it is a E. A is a degenerate, non-bonding degenerate, and E is a doubly bonded degenerate molecular orbitals. This is linear molecules and this is triangular molecules. This is linear molecules. We observe that 1 sigma, 2 sigma, and 3 sigma, they will have the more energy as compared to triangular ion. The 1s sigma orbitals after bending, the energy will be decreases as like this. But as twice sigma molecular orbitals is some times the energy will be increases and is going to shows character as like the antibonding molecular orbitals, and this is high sigma orbital molecular, they will be decreases. So A to E. As the bond angle at 180 degree in linear molecules, S3 molecule changes to 60 degree in triangular ions, right? And the energy of the molecular orbitals also changes. The sigma orbitals in linear into A to E can be changes, right? So such a method or such process can be described by using the extended to obtain molecular orbitals for molecules using these three or more atoms, but process will be same by using some of this method as like these such a steps can be includes. Firstly, to determine the point group of the molecules. Next steps, assign x, y, z coordinate to the atoms. But the general rules, all the examples is that the highest order rotation axis of the molecules can be chosen and the z axis of the central atom chosen as the z axis of the central atom. Third step, the atomic orbitals of the peripheral atom combine and to form group orbitals. And this is equivalent to finding the symmetry of the group orbitals or the symmetry adopted linear combination of the orbitals. And next step, combine the atomic orbitals of the central atom with the same symmetries as those found to step 3, that is group orbitals. So such parts we have seen in last lectures, and therefore the combined atomic orbitals of the central atom and those of the group orbitals with the same symmetry and similar energy to form these molecular orbitals. The total number of molecular orbitals formed equal to the number of atomic orbitals are used from molecular orbitals. And next, the process used in creating molecular orbitals is to match the symmetry, which are very important symmetries of the groups orbitals and symmetry of the central atom orbitals. If the symmetry match and energy are not to match, then there is interactions, both bonding and anti-bonding. But if it is not interactions, that times the symmetry does not match and energy also does not match with each other by those molecular orbitals. Therefore, such a process or such steps which are used for the matching molecular orbitals which they greater overlap between these molecular orbitals. Okay.